Where you are. Could be morning still, but for those of you who don't know me, my name is Trevor Trainer. I'm the president and a building science specialist with Boating Building Science. And today I'm going to talk about vapor flow, vapor movement in buildings. So I'm just going to shut off my camera because that's been kind of messing with the audio a bit, and I'm going to share my screen, and hopefully that works out. We can get started. Okay, that seems to have worked. Okay,
Yeah,
great.
you're good.
Perfect. Okay, so today we're going to talk about vapor flow and vapor movement in buildings. It's something that we don't usually, hear about a lot. Air tightness, obviously, is a big issue that we hear a lot about. Thermal performance, R values and stuff like that. But actually, vapor movement can be really important and something it's really good to have a more full understanding of as we are, designing buildings, evaluating buildings, and working with, especially residentially. We know what the code says, but I think it's good to have a deeper understanding. So we're talking about water vapor in air, and if we look at, the what air and atmospheric gases are made out of, we're in this little slice here of all others for water molecules. So in the grand scheme of things, it's pretty small compared to the other elements in the atmosphere, but it's pretty important when it comes to moisture durability in buildings. So mostly we're talking about water vapor as individual molecules of water suspended in air. And just for reference, it takes about 1.67 times 10 to the 21 water molecules to make one water droplet. So obviously this isn't something we can see. This is something that exists in the air, but as we get into things like condensation, we can start to see it and start to see the effects of it. And can be quite negative on our buildings if we don't understand it and control it properly. So vapor diffusion is the net movement of water vapor from an area of high concentration, so this side in this example, to an area of lower concentration. So it occurs due to random molecular movement. So if you remember science class and the movement of molecules, they're just randomly bouncing around here. I don't have an animated version of this, but once they bounce around and find a pore or some other way to get through a material, they will pass through. The rate of movement from one side to the other across a material is a function of two things: the concentration difference, which we're going to call the vapor pressure difference. We'll talk a lot about that. And the vapor flow resistance of the material that's separating the two of them. So those are the two main things that affect how quickly vapor can move across a building material. So the greater the concentration of vapor pressure, or the greater, the vapor pressure difference, so the concentration difference from one side to the other, the greater the flow of moisture through a material, and also the lower the resistance, the flow resistance of the material itself, the greater the rate of movement from one side to the other. So those are the two major elements that we'll sort of work with and deal with when we're talking about vapor flow across a material. So how do we describe vapor flow resistance in materials? A couple different ways. One of the problems with understanding this is that we use a lot of different terminology, and it's good to have a general understanding of it. So you'll hear the term vapor permeance and you'll hear the term vapor permeability. And they do sound pretty much the same and they're very close, but it's important to remember that vapor permeance is the property of a layer in a wall system. It's used to describe membranes and composite materials and other sort of homogeneous materials at a given thickness. So if you were to talk about, let's say, a vapor barrier, a sheet of polyethylene, you'd want to talk about vapor permeance. And same with any other sort of material that sort of comes as in one thickness. So it can't be used to calculate or predict the performance of that material at different thicknesses. So it's really only good for things like that just come in one thickness. Whereas vapor permeability is a material property, not just a layer property, but a property of the material we're talking about. And it's better to use to describe sort of homogeneous materials, things that aren't made of composite layers, but one thing, one material. And the useful part about vapor permeability is it can be used to calculate or predict the performance of that material at different thicknesses. So if we're talking about a concrete wall or a brick or a foam board insulation, vapor permeability can be really useful to understand, because as we add thickness, we have reduced vapor flow through it, and we can predict that using vapor permeability. So not to get it too much into the weeds here, but there are sadly different units that you're going to see out there, metric units and imperial units. Probably the most important thing to know about metric units, if you see, in the Ontario Building Code and the National Building Code, they talk about permeance in SI units, which is in nanograms of water per Pascal pressure difference per second per meter squared of area. Whereas in the US, and you'll see this in some materials where they'll say X number of perms, and those are usually what they're talking about are US perms, which is a different measurement altogether. It's the same, there are conversion factors to go between the two. But just to note that permeance in nanograms is different than US perms. Permeability in SI units, again, which is nanograms of water per Pascal per second per meter of thickness, is different than perm inches, which is grains of water, blah, blah, blah. It's really more important that you just know that when you're talking about the vapor permeability of a material, it's really important to understand what units it's being described in, because you'll see both of those out there. In all of our code language, it will be in metric, but in some material specifications, it'll be in imperial units. So a little bit of trickery there, just to make it a little more confusing for everybody. So how do we measure the vapor flow resistance of a material? There's two major ways to do that. One is called a wet cup test, and one is called a dry cup test. In a wet cup test, you place the test sample on top of a container that's filled with water. There has to be an air gap here because you can't have the liquid water touching the test sample, or we'll get into other things like capillary movement of water, which we don't want to deal with. So it has to be a small air gap. But essentially, once this sample is sealed to this container, you're going to end up with a 100% relative humidity condition right above the water and right below the test sample. Then we're going to place that sample into a chamber, a test chamber that has standardized conditions. Typically, that's 50% RH, 25 degrees Celsius. And so knowing those two conditions, we can determine what the vapor pressure is of each side of the material. So in a 100% RH wet cup sample, the vapor permeant, or the vapor pressure on the backside is 3,100 pascals, and the vapor pressure in the chamber is 5,184 pascals. And so based on those numbers and how quickly this water evaporates from the container through the material into the room, we can measure that vapor permeability of that material over time. Depending on how vapor permeable this material is, this could take weeks, or this could be done in a couple of days. Sorry, I saw a question pop up, but then it went away. Where is that? Is that in the chat? Yeah, okay. Is there a certain temperature that the tests are conducted at? Generally, it's standardized to 25% or 25 degrees Celsius, but it could be done at any temperature, because whatever temperature you choose is going to create a different vapor pressure, which we're going to talk a bit about later. And it's really that moisture movement per area per vapor pressure difference that we're worried about. So there is, they can be done at different temperatures, and typically the vapor permeability of a material doesn't change with temperature. The other way they can do the test is called a dry cup test. So instead of putting water in a container, we put desiccant in a container. And what desiccant does, it can draw all the moisture out of the air above it and store it safely there. So what that does, it creates a 0% RH condition between the desiccant and the material. And under the same chamber conditions, this sample will start picking up moisture due to vapor movement from the chamber into the sample, and it will start to gain weight. So this sample will lose weight over time. With the wet cup, this will gain weight over time. And again, depending on the vapor permeance of the material, this could take a couple of days to a couple of weeks or a month to do. One of the limitations of the dry cup is the desiccant can only hold so much moisture. And so you have to be able to make sure you collect your data points within the range of what that desiccant can hold, because eventually it will fill up and this won't be 0 RH anymore after a little bit of time. Okay, so that's how we measure it. What are we talking about for materials? Here's some typical materials and what their vapor permeability is. So let's look at what we know as a vapor barrier. Typically, it's 6 mil polyethylene. You can see where its vapor permeability in nanograms is down here in the 4 or 5 range. Other things we might be interested in. Vapor barrier primer is something I'll talk a little bit about. And it has a vapor permeance around 35 nanograms. And the red line you can see here is what right now the NBC has as a requirement to act as a vapor barrier. We have other things that can act as vapor barriers, including 1/2-inch plywood or OSB. They have vapor permeances, significantly below this requirement. Here's a specialized product called Certainteed Membrane, which is a smart vapor barrier, which has different vapor permeance characteristics at different RH values. But I think this is the dry cup value here, which is just below. You can tell it's been kind of engineered to land right below this requirement. Spray foam, typically 2-pound spray foam. So your high density spray foam at 2 inches of thickness is below their NBC requirement for it as a vapor barrier. 1/2-pound spray foam, however, the low density spray foam is significantly higher vapor permeability and does not qualify as a vapor barrier. EPS, so expanded polystyrene foam board insulation, is quite a bit above at 2 inches, quite a bit above that level. Whereas XPS, extruded polystyrene at 2 inches, is significantly below. Polyiso styrene, which is another board insulation, is above, but it usually has a foil facer. So this foil faced version of polyiso would be well below. So the other interesting thing in our codes in Canada, we have this one requirement. In the IRC, in the International Residential Code, there's a lot more subtlety to it, and they define class 1, class 2, and class 3 vapor retarders, they call them. So something that can slow down vapor, and they can call out different times when a class 3 might be fine, depending on different conditions, mostly the climate, or maybe a class 2 would be fine, maybe class 1. So there's not much subtlety in our codes here in Canada, but in the US and in the international codes, there's a lot more subtlety to it. And I think you'll see why that's a good thing as we go forward here. So one thing I like to always bring up early on is the difference between relative humidity and vapor pressure. So relative humidity is a measure of the amount of moisture contained within air relative to the maximum amount of moisture that the air can hold. And so what that means, at warm temperatures, air can hold a lot of moisture, and at cold temperatures, it can hold very little. And the RH is sort of that relative to the maximum amount it can hold. What is it? Whereas vapor pressure is the absolute amount of moisture contained within the air. It's not relative to anything. It's just the number of molecules essentially in the air. And so cold air, for example, with a high relative humidity can have a very low vapor pressure. It will have a very low vapor pressure, whereas warm air with lower relative humidity can still have a higher vapor pressure. So the two are related, but they don't, they're not directly related. And we'll talk a bit more about that. The important thing to remember in terms of vapor flow, when we're talking about vapor barriers and vapor flow, is that vapor flows from an area of high vapor pressure to an area of low vapor pressure, not necessarily high RH to low RH. And the relationship between relative humidity and vapor pressure can be explained in something called the psychrometric chart. So if you've ever seen this before, there's a lot to it, and it looks very complicated, and it can be, but I think there's some really simple things we can take away from this chart, which describes the relationship between the temperature of air and the vapor pressure of air and the relative humidity. So those three things are kind of baked into this. So what you'd see at any point on this chart, well, here, let me give you an example. So in this case, we're going to have two things we're going to look at. We're going to look at the normal conditions of outdoor air. So let's say it's -5 outside, okay? And when it's -5 outside, you'll notice that the relative humidity would be very high, 90 to 95% relative humidity when it's -5. And so if I go from -5 and I move up, each of these lines, red lines, represents a different relative humidity level. This one represents 100%, this one 90%. So if we were to look at -5 degrees, 90% relative humidity air, we go up until we meet this line, which doesn't quite meet there, but right about there. And if we were to take that point and go straight across to the vapor pressure side of the graph, we get around, a little bit over 3, and this is in millimeters of mercury, but I've turned this into pascals of pressure to show you the difference. If we were to take typical indoor air, let's say we have 20-degree air indoor in the winter, and let's say it's 40% relative humidity, which is a little bit high, but still realistic. I've seen it more than once. If we were to take that condition and go across, we're going to have something more like a vapor pressure of 7 millimeters of mercury. If we were to do the conversions to pascals, the difference from indoor to outdoor in this condition is about 533 pascals. And it's an outward direction flow. So higher indoors, lower outdoors. And that's the pressure that would try and push moisture from inside of our house to the exterior. So that's the sort of what you would probably see in something like a Toronto winter condition at -5. Let's look at that somewhere else. Look at that in Winnipeg. So the indoor conditions, let's say, stayed the same. So we'll leave that the same. But in Winnipeg, let's say today, it's -20. And if it's -20, it's basically 100% relative humidity, pretty close to it. And if we were to follow that across, we're going to see that we're down in the, who knows what that is, less than 1 millimeter of mercury. And the pressure difference from inside to outside in Winnipeg at -20 is about 866 pascals pushing outwards. And so this starts to speak to a couple of things. It starts to speak to why climate matters when it comes to vapor control, right? Because there's a lot more vapor pressure pushing vapor outwards in a Winnipeg winter than a Toronto winter. It also speaks to interior relative humidity levels. Because if we were to drop this Winnipeg interior RH down to 30%, then we would drop this red line down to about 5. We'd cut that by about, a quarter again. So those are some things we can control to help us control vapor flow. And then here's oops, sorry, jumped ahead. Here's what some of the conditions look like for Toronto in the summer. So let's say we keep, we're a little higher, like 21, 22 degrees in interior air temperature. and 60% relative humidity. That's pretty normal. But outdoors, we're at 25 degrees Celsius and we're at 80% relative humidity. So this is not unusual conditions for a Toronto summer. And now what we have a almost 800, well, we have over 700 Pascal difference, but now it's in the opposite direction. It's trying to drive from outdoors to indoors. And so that's sort of the problem we deal with in mixed climates, is that for a certain point of the year, vapor's trying to drive outwards, and for another part of the year, it's trying to drive inwards. And depending on where you are in the country, where you are in, in North America, this can be very different. So here's what a graphic put together of sort of hourly, sort of continuous vapor pressures for Toronto. The blue is outdoor, exterior vapor pressure, and the red is a predicted interior vapor pressure. And so what we start to look at is how much of the year is the exterior vapor pressure below the interior and how much is it above. In this case, it's about 86% of the year that the vapor pressure is pushing from inside to outside, even in Toronto. If we were to go to Houston or somewhere, this could be very different. This could be almost reversed, where it's flowing the other direction 86% of the time. When we see here in the summer, June, July, August, there's certainly areas where, just checking, okay. There's certainly times of the year, especially in Toronto, where we have a reverse flow. And that's about 14% of the year where the vapor is trying to flow from outdoors to indoors. And so this starts to have implications on sort of what we use as vapor barriers and where we put them and how effective they are. So we look at the same data for Winnipeg. A lot more of the year, there's an outward vapor drive, right? And there's only quite a bit smaller percent. Only 9% of the year is there an inward vapor drive in something like Winnipeg. If we were to go into an even colder climate, then you'd see this almost be entirely outward vapor drive at almost all of the year. If we were to look at, say, in Iqaluit, I've done this for Iqaluit, it's almost 100% vapor flow from indoors to outdoors. And so that sort of matters when it comes to the performance of our building enclosure and how we design our vapor barrier. So this is another way I'm just going to show how vapor moves through materials. First, I want to talk about like our old houses. So we build houses in North America in cold climates for a long time. I'm not sure how many years, hundreds, with no vapor barriers whatsoever, right? And we tend to not have problems with those buildings. Question before I move on to this. Let's see. Although vapor flow depends on vapor pressure, not RH, can we still infer the flow from RH? You really can't infer the flow from RH other than knowing that the higher the interior RH, the higher the vapor flow. The problem being, if we were to look at, let's say, if this was inside during the winter, 20 degrees, 40% RH, and this was minus 10, 90% RH. So now we have a 40 to 90% RH difference, but we're not going to see movement from 90% to 40. We're going to see it the other way because of vapor pressure. So you really do have to understand how temperature, the air temperature is playing into this. And that's what oops, sorry. Let's see if I can go up. Nope, I can't. That's what the psychrometric chart does for us. It takes that out of play. It takes into account temperature. And that's how, you know, that's how we relate RH and temperature to vapor flow. So you can't just infer much from RH.
Thank you.
Oh yeah, no problem. We'll talk a little bit more about that too as we go. Okay, so we're talking about these old houses. Say, in my neighborhood, there's a lot of old brick, three-layer brick houses. They don't have any vapor barriers in them. Obviously, at that time, that's not the way we built. But they don't have moisture issues due to vapor flow. And the reason that is because when we have a monolithic material, a monolithic wall in this case, with no cavities in it, the material's the same throughout, and whatever rate moisture is able to enter the wall, it is able to leave the wall at the same rate. So there'll be no accumulation of moisture in a wall like this. It enters and leaves at the same rate. It never builds up inside due to vapor flow. It could build up on the outside due to rain and other things. Air leakage is a whole other thing, but due to vapor flow, it will never build up inside a monolithic wall like this. And here's the reason. We look at this monolithic wall. So this is a triple wide brick wall. If we look at the temperature profile across this wall, that's the red line. Basically, you have an even drop from whatever the temperature is inside to whatever the temperature is outside, right? And you also, from an R relative humidity standpoint, I guess, no, next we'll talk about the vapor pressure. And so from a vapor pressure standpoint, we have to get from wherever we are inside to wherever we are outside, and it's a linear relationship. And so vapor pressure follows temperature perfectly, essentially, in this wall, and therefore RH never jumps up above whatever it is outside. It's just a straight line relationship. So what we have to start worrying about later is when temperature and vapor pressure don't follow each other in this way. So in this case, the surface inside, inside these materials will never be higher RH than the exterior under winter conditions. So you'll never have moisture accumulation due to vapor flow. Now let's look at what I have at my house, and I have a 100-year-old house, but it's not brick like that. I have a cavity wall with brick on the outside. I have interior cement plasterboard on the inside, and I have board sheathing on the outside. So if you've never seen board sheathing, it's literally boards. Instead of using plywood on the outside, we use whole boards, and they typically have a 1/2 inch to 3/4 inch gap between them. And so because of that, if we look at the vapor flow characteristics of these two things, the interior plaster is actually more vapor closed, less vapor permeable than the board sheathing. So whatever moves from inside the house into this wall cavity, whatever rate it can flow in, it can actually flow out faster than that. So we'll never get a buildup of condensation due to vapor flow inside an old wall that has board sheathing, because it's very vapor open on the outside. Even though cement plaster isn't particularly good vapor barrier, it's the most vapor closed portion of this wall. So it's the thing that regulates how much moisture gets into this wall cavity, and it can get out faster than it got in. So now things get a little more complicated when we look at our temperature and our vapor pressure profiles. So in this case, if we had no insulation in this wall, it was just a cavity. Well, air is a type of insulation, I suppose, very limited. But eventually, the temperature has to go from indoor conditions to outdoor conditions, and it's basically going to do that in a linear fashion. Okay, so there's no layer in here that's really more, significantly more thermally resistant than anything else, so you get this linear relationship. On the other hand, your vapor pressure, you've got two things. The air has no resistance to vapor flow. The plaster has a certain amount, and the board sheathing has a certain amount. So we've got to get at some point from indoor vapor pressure to outdoor. And if what's on the inside is even a little bit more vapor closed or less vapor permeable than on what's outside, you'll get a bigger drop across this first material than you will across the second material. And so what that does to our RH, it means that our RH has no reason to really go above the exterior RH conditions, because it's losing, we're basically heading for the outdoor condition. And we'll see how that's different in a minute. And the only reason I put this one up here is if you have insulation in this type of a wall, it doesn't really change much. It's the same thing in that you really don't have much reason for relative humidity to go up much above exterior conditions when you have more vapor open material on the outside, less on the inside, or more vapor tight on the inside. So that's how old walls worked. And that's how a lot of them are still working today without vapor barriers and without problems due to vapor flow. Lots of other problems, probably air leakiness and poor thermal performance, but they don't have any problems related to vapor flow. And so what changes in a modern wall is that now we're not using this board sheathing anymore, right? And we're not using plaster, cement plaster anymore. So we're using drywall, and we're using OSB or plywood sheathing. So let's look at this as if let's just build this wall like we would today, except without a vapor barrier. So what we'll see is that the drywall with latex paint is the most vapor open part of this wall. The plywood sheathing or the OSB sheathing is quite a bit less vapor permeable than the interior drywall. And so what's going to happen is we're going to get a large flow of moisture into the wall cavity, and it's going to leave slowly. And so you end up accumulating moisture inside, between these two layers. And so as this occurs, the relative humidities are going to drive up, and we're going to have condensation problems. So we can't just keep building without vapor barriers if we're going to go to drywall and OSB sheathing in a cavity wall. What we need to do is add this extra layer, right, behind the drywall in this case. There's other ways to do it, but this is the most typical way to do it. If we add this, if this yellow line is our 6 mil polyethylene, what that does is dramatically slows down the movement through the drywall and through this poly, meaning water vapor is moving very slowly into this wall cavity. And even though OSB and plywood aren't very vapor open, they're quite a bit more vapor open than our polyethylene. And so moisture doesn't accumulate in this wall cavity because it can leave faster than it comes in. And so now we get into sort of more complicated versions of this diagram. But oops. Here's the important part. We still have our temperature dropping across linearly, right? Now, though, we have in this case, with no vapor barrier, we have a little bit of vapor pressure drop across the drywall and paint, but most of it occurs out here. So we still have high vapor pressure out here where it's cold, which drives our RH, our relative humidity, very high at this surface. And that's exactly where we get condensation problems. If you were to build a standard stud wall with drywall and OSB and no vapor barrier, even in Toronto, this is what would occur. You'd get condensation on the backside and moisture accumulation inside this cavity. And so by adding this vapor barrier layer, so that's this yellow line in this case, what we've done is make our vapor pressure drop. Almost all of the drop occurs across that. It's supposed to keep going. But almost all the vapor pressure drop occurs across the vapor retarder, or in this case, the poly vapor barrier. And so by the time we get to the cold exterior cladding, Oops, sorry, jumped ahead. There's not much moisture here to drive condensation problems. So your RH won't jump up above really the exterior conditions. In this case, we'd say 90. So that's why in the past, we didn't need vapor barriers, but now we do. So yeah, so vapor flow in new walls, vapor barriers are necessary, or are they, I guess is the question. So there's other ways we can deal with vapor. This is the exact same drawing we showed before. This is one way to do it. We can deal with vapor using a vapor barrier, and we won't have condensation issues due to vapor flow. Or we could do, there's another way we could do it, which is to start adding exterior insulation to the outside, warming up our condensation plane. If we were to add just a little bit of exterior insulation, depending on where we are, let's say in Winnipeg, if we were to add R5 exterior insulation in Winnipeg, we do warm up this surface, but probably not enough to avoid condensation. So we would still have this peak, this spike that might hit 100% RH if we don't have enough exterior insulation. But if we add enough exterior insulation, let's say we added R10 and we had no vapor barrier, we would probably not have any moisture. At least in Toronto, I know R10 will work perfectly well. In colder climates, you might need more to get the same effect. But the idea being that even without a vapor barrier on the inside, you can avoid condensation due to vapor flow by just warming up this condensation plane, this OSB that is not as vapor open as our old board sheathing used to be, right? So that's another way to deal with it. We can deal with it by stopping vapor flow. We can deal with it by warming up our condensation plane. In this case, what we're really doing in this case, if we have no vapor barrier, what we're really doing is turning our exterior OSB or plywood into our vapor barrier. And to do that, we just have to make sure it stays warm enough to avoid condensation. And we do that by just adding exterior insulation. So there's other ways to deal with vapor flow, and it really is a combination of temperature and vapor pressure that we're playing with. So what I try and promote here is that we need vapor control for sure. We need vapor control strategies, but we don't necessarily need polyethylene. So that poly vapor barrier on the inside. So let's look at, this is results from a hydrothermal modeling study. And what this is showing, so these percentages are wood moisture content of the sheathing. In this case, it's OSB sheathing. And these are the months of the year across the bottom. And we're gonna look at a couple different ways. If we were to take that 2x6 wall with no vapor barrier and OSB sheathing in Toronto and just run it, what we're gonna see is that from November through almost June, there's gonna be a rapid increase in moisture content in the sheathing. And that's due to that condensation due to vapor flow that we're seeing. So this doesn't even include anything due to air leakage condensation. This is just vapor flow. So you could see that you could definitely have a real problem because anything above 20% moisture content starts to become a high risk of mold growth, rot, and decay. And certainly above 40% would be a huge risk. So we can't just build Toronto with no vapor barrier. So what we usually do is we add this poly layer. So in the orange line shows, what if we just add that poly layer? If we just add that poly layer, no problem. It takes our moisture contents down to well below 20 throughout the year. But we do have other options, especially in the Toronto climate. What about vapor barrier paint? If you remember that chart we showed, vapor barrier paint is much more vapor open than a polyethylene sheet, but still can be used to control vapor. And here's what it would do. So that's the gray line here. And what it shows is that we still stay well below 20% moisture content in the Toronto climate just by using vapor barrier paint instead of the poly. And then the other option I just chose to show was, what if we were to add R10 of insulation to the outside, like we talked about? So no vapor barrier whatsoever, R10 insulation on the outside, and that's this light blue line. So we do get a little bit over 20 for one week or two, but generally also could be a very safe approach. The other thing I want to talk about is that not only, does the vapor permeance matter in the exterior insulation, but climate matters too, right? So we talked about this Toronto with vapor barrier paint, nice and safe in Toronto. We're take that just to Ottawa, not a big difference, but cold enough or a difference enough that vapor barrier paint starts to climb, our moisture content starts to climb above 20% through the middle of the winter. So this is getting into the zone where I wouldn't feel comfortable recommending this approach in Ottawa because of how much time it spends above 20%. If we were to also add R5 in Ottawa, so even just a little bit of exterior insulation and vapor barrier paint, you can see what that does. It actually improves it beyond Toronto's vapor barrier paint moisture content levels. So these things all interact with each other, and we can play with them in different ways to get the results that we want if we sort of understand how they interact. The other thing that matters is the interior relative humidity. So this is a really big issue in Indigenous housing where we get into overcrowded conditions. And we get a lot of moisture generation inside of a small house. And so what we can see here is just one example from Toronto. It's probably not as dramatic as it could be if we looked at it in a colder climate. But even just looking at Toronto, so the gray, again, was that Toronto with vapor barrier paint. So we still went well below 20. That's with a medium, what I'm calling medium RH. So that's, I think, 35% relative humidity in the winter. If we were to get that up to 40% relative humidity in the winter, that's the brown line. You can see just by going from 35 to 40% relative humidity in the winter, we start to drive the moisture content of our sheathing into this risky zone above 20%. And if we were to lower the RH down to 30% in the winter, that's the dark gray line, and we're even more safe than before. So it'd probably be more dramatic to show this with like a Winnipeg climate or something colder, and it probably will fix that for the next time. But you can see the effect that interior relative humidity has on the moisture inside of a wall system. That's kind of the point there. Okay, I'm just going to go quickly through the last little bit, and then we'll get to save some time for questions. So if poly works all the time from a vapor flow standpoint, that's great. Why not just use it all the time? Well, there are some issues. So 6 mil poly has a vapor flow resistance of about 1,000 times higher than the OBC requirement. And it can result in condensation due to inward vapor drive. So remember we talked about summertime vapor drives, and especially in below grade walls. This can be a real concern of inward vapor drive and condensation on the inside, on the exterior side of the poly during the summer. This can be, definitely an issue with any moisture storing claddings, so like brick or direct applied stone, or for the foundation walls. And also because polyethylene allows no moisture flow through it, essentially, it can result in a moisture trap for walls that have low perm materials on the exterior. So foam board insulation, as an example, we have to be careful that we don't end up with a double vapor barrier on a wall that has poly on the inside and foam board insulation on the outside. So real quick, let's look at vapor flow in a basement wall. So this is in the summertime. So we're below grade here. Even if it's, say, 22 degrees outside, maybe just below the surface of the ground, it's 20 degrees inside. Basically what we've got here, really high vapor pressures, because we have 100% relative humidity in the ground, in the soil. So really high vapor pressure. And we generally don't see much to stop the vapor flow going through the concrete wall. So this is our basement concrete wall, but we have a stud wall on the inside with poly, which is a very common approach. What we'll see is that all the vapor pressure drop occurs across that interior poly layer. And so we actually end up with a pretty high vapor pressure difference from inside to outside. And you can end up with very high and potentially 100% relative humidity conditions on the exterior side of this polyethylene sheet in a below grade well. So depending on how much moisture is in the soil, how much sun is hitting and driving moisture through, this can quite often result in condensation on the backside of this poly sheet if we use this approach below grade. And this is what the hourly vapor pressure looks like below grade. So we showed the above grade. And the big difference between above grade and low grade is this, how high of an RH we have below grade. And so that drives up our vapor pressure flow to inward for a lot of the, right from probably April, May through October. So that's a lot of time where vapor flow is trying to go from outside to inside. And if this condition is occurring through a significant amount of that, we could get a lot of moisture buildup in this stud wall that's inside of our foundation wall. Question I see here, what is the difference in moisture content? Rock wool versus polyglass versus polyurethane foam. Well, there's no difference in moisture content. Maybe you mean vapor permeability. If you do, then rock wool and fiberglass have basically no resistance to vapor flow. They're pretty much vapor open. Whereas all of your foam products, and especially polyurethane foam and XPS, have very high vapor flow. Oh, and steel panel would have zero permeance whatsoever. That's why whenever we're using materials on the outside of the building that have low permeance, like concrete board, siding, or steel panels, there always needs to be an air gap in there to allow that moisture to flow away, because that's essentially an exterior perfect vapor barrier, which we're trying to avoid. That answers that question. So yeah, just some examples of moisture flow in basements that I've come across in my forensic work. How do we avoid this problem? This is my favorite way to do it. There's other ways. Mine is to put a 1 to 2 inch layer of foam board insulation. It could be spray foam directly against the concrete wall, and then build a stud wall in front of that, and not use a polyethylene vapor barrier. And so what you'll see here is that all of your vapor flow drop, all of your vapor pressure drop, and therefore all of your relative humidity drop occurs across this layer. And so it's okay for it to have 100% moisture content right here where concrete meets foam board, because both of those are resistance to moisture. But by the time we get to any wood structure, we'll have much lower relative humidities. This is a much safer approach for below grade than only using this stud wall with no foam board insulation there. You know what? I think, yeah, okay. One more slide and then we'll take questions. And so the other thing to think about, we talked a bit about using foam board insulation on the outside and how that can be a good thing if you use enough. But if you don't use enough, you could end up with a double vapor barrier situation. There was a question about mineral wool. If we were to replace our exterior insulation, if we were to take out our foam board insulation and use semi-rigid mineral wool, you can start to see how quickly some of the differences here. So if we were to look at a wall with no vapor barrier, let's say we closed a wall in wet. Let's say it was raining for a month and then we closed everything in. If that wall had no vapor barrier, but it had foam board on the outside, this is how long it would take to dry out. So let's say it started at 30%. It would actually get wetter the first winter, and it would dry down eventually to 15% because that's drying inward with no vapor barrier. Similarly for, smart membrane will help drag that down a little bit. Vapor barrier paint will allow it to dry a little more quickly, and the smart vapor barrier a little more quickly. But what I wanted to really highlight here is this green line. So the green line is if we replace our foam board insulation with mineral wool, semi-rigid mineral wool insulation, now this sheathing can dry outward. And that's a much stronger process. And you can see how quickly we can dry out a wet assembly if we don't have anything on the outside preventing the drying. And so even if we were to, do that in January, but by the end of the first year, that wall would be dry. Whereas if we have foam board and combination of foam board and interior poly, we would have, it would take 2 to 3, upwards of 2 years before it dried out to a safe level. Okay, I have a section on code that I'm not going to do because you guys probably know as much or more about it than I do. And plus we're running out of time. And also plus it's kind of boring. So I'm just going to jump to the summary. Do we need a vapor barrier? No, we don't need a vapor barrier per se, but we need a vapor control strategy. We need to understand vapor movement and temperature and the interaction between RH and vapor pressure. What can we use as a vapor control layer? There's a lot of things we could use, and it depends on a lot of factors, including the climate, the interior conditions, what materials we have on the exterior side of the wall. Is that wall above grade or below grade? And how much exterior insulation do we have? All those things can play in and start to help us decide what is the proper vapor control strategy. Question. Oh, don't tape. No. So, okay, let me go back one. So the question, I guess, is don't tape the seams on the foam board to allow drying. That's not going to help. So remember that vapor flow, it's a surface area condition. So if you have 2 foam boards pressed up against each other or even gapped slightly, that's not really going to affect vapor flow through them. It's only the amount of surface area that gap represents compared to the rest of the wall. So taping seams or not taping seams, taping seams is not necessary to control vapor. If you're going to use it as air control, then you'll want to tape the seams. But leaving seams open isn't really going to allow much drying. Just, so you know. Okay, question time. And I see Claude.